Hi, I'm Michael Kearney on the University of West of England's Cybersecurity MSc, and today I'm going to talk over a summary of the Cybersecurity Analytics module. This module consists of 3 practical tasks. The first was using pandas and Python to explore web application security logs. The second task was using machine learning to categorize domain name generation algorithms into different malware families. And the final task was using the Detection Labs environment to explore some attack and defend techniques using Splunk. The first task used interactive Python notebooks and pandas to explore for signs of attack in web application logs. The task provided a Python notebook with a pandas data frame containing all of the application logs. It was our task to explore these logs and look for signs of attack. Initially I started digging into the data to look for any signs of attack, but a sort of scattergun approach proved very ineffective and I realised I'd have to be a lot more scientific. I therefore thought of 6 different attack scenarios that it may be possible to detect within this data. For each attack, I'll consider what sort of artifacts I would expect to see in the provided logs were that attack present on the network at the time. I would then hunt for those artifacts and make a conclusion as to whether I thought the attack had or had not occurred. A simple example is a DDoS attack, where we'd expect to see a spike in the amount of requests being sent to a server in a short period of time. This is easy to visualise and we can see from the data there is no clear spikes, from which we could draw the conclusion there was no DDoS present during this period. Taking a similar approach to brute force logons, we would expect to see a spike in the amount of post requests as the attacker brute forces a logon form. This is indeed what we see here in this chart of post and get requests to the server. This is clearer when we isolate the 401 unauthorized returns and just view them against the post requests. 3 attacks clearly stand out. Zooming to each and filtering just for the attacker's IP, we can see the moment when the amount of post requests start dropping and the attacker starts to use get requests to manipulate the accounts. I use this approach to find 3 different attacks present on the network. To record the attacks, I created a Python attack class with some helper methods to help extract some raw data from the data frames. To conclude, I exported the attack objects as machine-readable JSON format so they could easily be used by subsequent security tooling. And that brings us on to task 2, using machine learning to categorize the names generated by malware based on their domain name generation algorithm. The task provided a dataset of 24,000 different domains divided into 24 categories, that being 1 benign and 23 categories of malware. The task was to train and compare a few different machine learning models to predict to which class a domain belonged. To do this, I'll train 4 different models based on 4 different algorithms in sklearn. These being a logistic regression, support vector machine, random forest, and multi-layer perceptron, or otherwise known as a neural network. As the data provided only provides a single string for each domain, I'll first need to analyse the data and extract some numerical features from this, which can then be used to train our models. I extracted and visualised various features, including the relationship between the vowels and the consonants, the length of the domain, the top level domain used for each, and the amount of symbols used in each domain. For some models, I also added a character by character encoded vector, using the ASCII characters values for each character. For example, abc.xyz would translate to 97, 98, 99, 46, 120, 121, 122. This was added as additional columns to the end of each and used to train some of the models. Combining these data together, I managed to achieve accuracies of up to 90%. I wanted to follow further on this encoded vector idea and decided to try building a deep learning model using a more advanced tool known as TensorFlow. With this, I would pass in just the encoded domains and do no intelligent human feature extraction, leaving the model to define and extract the features itself. Here I come across a shortfall of my previous technique. When we previously spoke about the encoder, we hadn't discussed the impact of the scaler. This could distort the relative values of the letters within the vector. To illustrate this, let's take the example of 2 domains, AAAA.ZZZZ and MMMM.MMMM. If we fit the min-max scaler to these 2 domains and then transform each, we see that AAAA.ZZZZ translates to 0000111. What's interesting here is the dot and the A are translated as the same character once transformed. This distortion becomes more apparent when we look at MMMM.MMMM, which translates to 1110000. In this case, the same letter M has translated as both a 1 and a 0. This can be resolved by adding a dimension and conducting an additional 1-hot encoding. This is what has been done here. This graph represents a single domain. The x-axis represents the ASCII character value and the y-axis the position of a character in the string. Thus each value is always a 1 or a 0, so no scaling was required. You can note the dot as the outlier on the left-hand side. With this 2-dimensional encoding technique, I'm able to use a deep learning algorithm called a convolutional neural network. This works by scanning smaller filters over the image to look for certain patterns. The output from these filters produce new layers on which the process is repeated. The deeper into model the layers go, the more complex the abstract patterns and features that can be extracted. This visualization depicts how the initial layer of the convolutional network will scan its filter over our encoded domain. The model's architecture is made up of 3 convolutional layers, followed by 1 flattened layer. This then connects to a fully connected layer, very similar to the MPL classifier in sklearn. The model can thus be considered to have 2 sections, a convolutional section and a fully connected section. As well as this, I added 3 dropout layers to help prevent overfitting. These work by randomly removing some of the values during the training process. TensorFlow produces useful metrics during the training process which can be visualized to help understand and optimize the model. Here we can see how the accuracy increased and loss decreased throughout the training epochs. With this model I was able to achieve an impressive 91% overall accuracy, and as you can see from the confusion matrix, most of the families were predicted with 100% accuracy. Given more time and a larger dataset, I believe it will be possible to improve on the 91%. I'll be very interested to experiment with changing the shapes of the convolutional filters from squares to more abstract shapes. And that brings us on to the final task, using Detection Lab and Splunk. I used the Detection Lab's Terraform script to build the environment in Amazon Web Services. I also added a Kali instance and configured it so it could talk to the rest of the network. I conducted 3 different attacks on the Detection Lab machine, and then built dashboards to look at see the results for each one. The first attack was a simple credentials brute force. This was largely just to test the environment working. I then used MSS Venom to create a reverse shell payload and run that on both the DC and the Windows 10's machines. I used this to connect back to the Kali machine that I added to the network to run a reverse shell. The final attack, I used Mimikatz tool to dump the LSAS memory to grab the credentials. The brute force attack is fairly simple. We can view this by seeing a spike in the amount of failed logons on both this DC and Win 10. By clicking into this, we can view the individual logs. Here we can see the log message says it's a credential logon and the status shows failed. We can see from the status code this is a 4476 message from Windows security logging. Detecting the MSF Venom reverse shell is a little more complex. I found the best indicator to be the base64 encoded pipelines. Detecting this activity on a pipeline, I can then click on the graph to use a token to pivot into another graph where I'm now looking at network connections from Sysmon. And by doing this, I can easily spot over a set period of time the 4444 connection, which is in fact the MSF Venom reverse shell. If I explore the raw data that made up the base64 encoded pipeline search, I can open one of the logs and see in the message field, if I scroll along, as part of this long message, I will see the term base64 encode, which you can see I've highlighted there. As we know what Mimikatz does, it accesses the memory for the LSAS process in order to dump the credentials. In theory, therefore, it should be easy to find this behavior in the logs. To assist with this, I turn to one of my favourite resources for Windows threat hunting, the SyAn's Find Evil No Normal. Here I can look up the LSAS process, which I see here. I can also view that there should be one of them and it should be running as a local system account. Thus, in theory, I should be able to look for all process memory accesses that are non-system accounts that try and access the LSAS memory. And this is in fact what I did using Sysmon to create this dashboard here of suspect LSAS accesses. As you can see, it has spotted them. However, if I switch this to the last 7 days, it shows no data found. Now I have used Mimikatz in the last 7 days, and in fact, if I look at the graph on the right, I can say that this process here was in fact Mimikatz that I had renamed. So why did this not display? We know from the Detection Lab website that Detection Lab uses the system modular configuration, which we can now view on GitHub. If we're looking for process accesses, we know this is sysmon event 10, so we can look up the rules for the process access sysmon event 10. By scrolling through this, we can see an interesting file here called exclude LSAS noise, and in it we can see some file names are excluded and they are an ends with, not a fully quoted file path. Knowing this allows us to rename Mimikatz and use it without triggering a sysmon event 10 on the LSAS memory. This highlights the importance of fine-tuning and configuring your sysmon and logging for your specific environment. Overall, this module has taught me how cybersecurity analytics requires a fine eye for detail. You'll often be presented with vast amounts of data, and stumbling around in the dark hoping you might happen across an attack is not a valid strategy. Instead, it is critical to understand how the attacks you're trying to defend against work and what artifacts they may leave on the data sources you have available. You're then able to optimize your defenses and fine-tune your alerts for exactly what it is you're looking for. This then gives you the power to spot the needle in the haystack and detect complex attacks as they happen.